Okay, before we get started, I've got an announcement that probably only pertains to some of you, but I'm going to tell everyone here anyway because I don't have a choice. So this is kind of a long story, but over 30 years ago, there used to be a Methodist hospital in Mitchell, and it was just to the west of campus here. It's over by where the Davidson County Public Service building is located now. And it was actually shortly after I started teaching here, the Avera Queen of Peace Hospital bought out the Methodist Hospital. And when they did that, the trustees for the Methodist Hospital was given a large payment for the sale of the Methodist Hospital to Queen of Peace. And since they were, and then Queen of Peace decided to close down the Methodist Hospital. So the board of trustees for the Methodist Hospital didn't know what to do with the money. So one of the things they did is they donated a large lump sum of money to Dakota Wesleyan University for education of students that were going into some aspect of medicine. And so what they did was they took that endowment and they divided it up between three departments. They gave some of the money to an endowment for scholarships for nursing. They gave some of the money to an endowment for scholarships for athletic training, and then they gave another one for biology, biochemistry, chemistry majors, any other major, okay? So if you're a nursing student, they give out 2 or 3 scholarships to nursing students every year. Athletic training, I think they give out 3 scholarships for athletic training students. And then all the other majors like biology and biochemistry and psychology, they give out 2 scholarships. The amount is a little bit larger since they only give out 2. So I sent out a couple of emails in the past week with the application. To be eligible for, it's called the St. Joseph Hospital Scholarship, you can't be a nursing student or athletic training or a pre-athletic training student because they have their own scholarship, okay? So this is just for biology, biochemistry, psychology, chemistry majors who are going into careers related to healthcare. So that includes medical school, it includes students planning to go in becoming a physician's assistant, chiropractic medicine, occupational therapy, anything medically related, okay? So the reason I'm mentioning this is that those applications are due soon. Okay, they're due, I think, like tomorrow. So some of you may have already applied, and that's good. But if you would like to apply for it, I think the scholarship is over $1,000. Only only certain majors at DW are eligible for it. So if you apply for it, there's a pretty good chance that you might get it. Not guaranteed, but there's a good chance because the pool of students that are eligible is rather small. Okay, so if you think you might be eligible, take a look at that email. I sent out another reminder this morning, so take a look at it, and it shouldn't take too long to apply. The criteria that's used to decide who gets the scholarships include the student's cumulative grade point average, and you have to write a short essay as to why you want to go into your chosen field of medicine. Shouldn't take too long to do that, though. I know the committee is made up of people from biology, chemistry, math. I think those 3 departments has selection committee members. And they base their decision, they base it on both cumulative GPA and the essay. They give about equal amount to both. So I've seen Some years I've seen students that had a lower GPA that got the scholarship because they wrote a better essay. So, you know, take your time, do a good job if you're gonna, writing the essay if you're gonna do that. Okay. Athletic training, I think athletic training professors, they just pick the 3 to give the scholarship. There's no application for it, I don't believe. Nursing, I'm not sure how they do it. I think they just pick the students they give the scholarships to. Nursing has lots of scholarships, so there's a lot of other ones that nursing students are eligible for too. So I thought I'd mention that. Also, I sent out an email to some of you for a math and science honor society called Sigma Zeta. It's free, there's no obligations. You need to let me know right away if you want to join that. It's kind of like National Honor Society, except there's no service requirements or anything to do. And the biology department pays the one-time national initiation fee, so there's no cost to the student. So check your email, reply if you get a copy of that. Okay. All right. So today I'm going to start out by talking about some basic laws and concepts of gases, because the respiratory system involves taking in and blowing out gases. And there's about 3 different gas laws that apply to the respiratory system. And then we'll start looking at gas exchange, which really is a pretty simple process since it just involves simple diffusion. So there's not a whole lot to say with gas exchange. Shouldn't take us too long this week to get through that part of chapter 22. And then finally we're going to talk about transport of respiratory gases in blood. And that'll be the last part of chapter 22 that we covered. So, as I said towards the end of class on Friday, airflow is governed by most of the same principles that govern blood flow. That is, blood flow is directly proportional, or airflow is directly proportional to the pressure difference between opposite ends of a tube. Okay, so air always flows from the area of high pressure to low pressure, just like blood. But it's also inversely proportional to the resistance. The resistance is the impediment to the flow of air. And that depends primarily upon the diameter of the airway. In general, the smaller the diameter of the airway, the more resistance. The greater the resistance, the less the airflow, because resistance is inversely proportional to airflow. So the flow of air is proportional to delta P, which is the difference in the pressure between 2 points in the respiratory system, divided by the resistance. Those are the same principles that govern blood flow. Now, there's several gas laws that have an effect on ventilation or breathing. The first one is called Boyle's Law. And Boyle's Law states that at a constant temperature, the pressure of a given quantity of gas is inversely proportional to its volume. So as volume increases, pressure decreases. As volume decreases, pressure increases. So if the lungs contain a quantity of gas and the lung volume increases, then the internal pressure of the air in the lungs is going to decrease or fall. Okay, that pressure inside the lungs is called the intrapulmonary pressure. Intra means within, and pulmonary refers to the respiratory system. And if that pressure falls below atmospheric pressure, then air is going to move into the lungs. And that's what causes inspiration, the inspiratory phase of the respiratory cycle. If the lung volume decreases, then the pressure is going to increase. When the pressure increases above that of the atmosphere, then air flows out of the lungs and back out into the atmosphere. And these pressure changes, as we saw last week, are caused by contraction and relaxation of certain respiratory muscles. Okay? So what happens during inspiration, you can see what happens during inspiration down here in the lower left. So during inspiration, what happens is the external intercostal muscles contract and elevates the rib cage. And so when the ribs are elevated, it's sort of like lifting up the handle of a pail, like an old-fashioned milk pail. When you lift up the handle of the pail, that handle moves forward and up. When it moves forward, that expands the your chest. And at the same time, the diaphragm contracts and it flattens out and it drops downward. That increases the lower part of the thoracic cavity. So during quiet breathing, the external intercostals expand the rib cage upward, and the diaphragm expands the lower part of the thoracic cavity downward. Those both serve to increase the volume of the thoracic cavity, and so the air pressure drops. And that's what causes air to enter the lungs. And then, when the diaphragm relaxes, the diaphragm moves back up to its resting position, which is more dome-shaped. And so when it relaxes, it actually moves upward. And that decreases the volume of the lower part of the thoracic cavity. And when the external intercostals relax, then the chest wall goes back to its original resting position. So it recoils, and that decreases the volume of the thoracic cavity. That decreased volume causes an increase in pressure inside the lungs, and that causes you to exhale. That causes the expiration phase of the respiratory cycle. Okay? So that in a nutshell then is how breathing occurs. Now, another law that does have a small effect on breathing is called Charles' law. Charles' law states that a given volume of a gas is directly proportional to its absolute temperature. So as temperature goes up, the volume of a gas will increase. So on a cool day of about 60 degrees Fahrenheit, that's actually warm. That would actually be warmer today than it is now. Inhaled air will increase in temperature by 21 degrees when it enters the body, because our body temperature would be higher than the air temperature. And so inhaled air is warmed up to 37 degrees Celsius, which is about 98.6, which rounds off to 99 degrees Fahrenheit, by the time it reaches the alveoli. So if you inhale 500 milliliters of air, which is a half a liter, that will actually expand to 536 liters. And so that also helps to inflate the lungs. That just because of the thermal expansion of the air, that helps to cause the lungs to become inflated. So pressure is one important determining factor of airflow, but resistance is the other. The greater the resistance, the slower the flow. And there are three factors that affect airway resistance. The number one factor is the diameter of the bronchioles, because the diameter of the bronchioles can be changed because there's smooth muscles in the walls of the bronchioles. Those are the smaller airways. The diameter of your larger airways, like the trachea and the primary and secondary and tertiary bronchi, those can't be changed. Their walls are too thick and too rigid. But the bronchioles, the smaller branches, the diameter of those can be changed by changing the amount of sympathetic stimulation to that smooth muscle. The more sympathetic stimulation, the more bronchodilation occurs. The bronchioles expand in their diameter. So bronchodilation is an increase in the diameter of a bronchus or a bronchiole. Either epinephrine or norepinephrine from sympathetic stimulation will stimulate bronchodilation. So one situation where that occurs is if a person is exercising. When you start to exercise, your body's demand for oxygen increases. So and one of the things that happens during exercise is there's an increase in sympathetic stimulation. And that sympathetic stimulation of the bronchioles causes bronchodilation, causes them to expand. That makes it easier for you to take air into your lungs, which makes sense because you're going to need more oxygen when you're exercising. Okay? Bronchoconstriction is a decrease in the diameter of bronchus or bronchiole. Activation of the bronchioles by the parasympathetic stimulation, that's going to cause bronchoconstriction because when you're resting, you don't need as much air. So the diameter of the bronchioles will decrease in order to match airflow to blood flow. So in addition to parasympathetic stimulation, there are a number of chemicals that can cause bronchoconstriction. Histamine is one of them. Histamine is a chemical that's released by tissues that are being damaged. Also, cold air and chemical irritants can cause bronchoconstriction. Okay? That's what happens. Bronchoconstriction is what happens when someone's having an asthma attack. Because what's happening is a chemical or an irritant like pollen causes your airways to release histamine. It's a reaction to that pollen or to the chemical, and that causes your bronchioles to constrict, and that makes it harder to breathe. That's what happens when someone has an asthma attack. The asthma attack is when your airways overreact to a foreign stimulus like pollen, and it causes more bronchoconstriction than what you need. Okay, now a third factor that affects resistance is called pulmonary compliance. Pulmonary compliance refers to the ease with which the lungs can expand. And that affects the lung volume that results from a pressure change. So the less pulmonary compliance you have, the less that your lungs are going to be able to expand, because decreased pulmonary compliance makes it harder for the lungs to stretch and to expand. So compliance generally in a young healthy person doesn't change very much from day to day, but it can be affected by certain pulmonary diseases. For example, emphysema or COPD, congestive obstructive pulmonary disease, can cause lung tissue to be damaged, and the lung tissue gets replaced with scar tissue. And scar tissue has less pulmonary compliance, so it's hard. Scar tissue is harder to stretch, and so that's going to decrease airflow. It's going to make it harder for the lungs to inflate. Now, another factor besides the diameter of the airways and pulmonary compliance, is the surface tension in the alveoli, in the distal bronchioles. And the reason surface tension of the alveoli and the bronchioles is a factor is that all the respiratory surfaces in our respiratory system are lined internally by a thin layer of water. There's a very thin layer of fluid. And water creates a surface tension. And if that surface tension gets too high, then the alveoli will collapse. And once they collapse, because of that surface tension created by the water, then it makes it hard for those alveoli to inflate again. In fact, it may become impossible for those to become inflated again. And that surface tension is actually caused by the attraction between the positive and negative portions of the water molecules, because each water molecule has a positive and negative charge. And so the positive charge of one water molecule is attracted to the negative charge of the other. And so, for example, let's say this is an alveolus here. Okay, you've got water lining the alveolus, and if you have a positive charge here on a water molecule and a negative charge over here, those are going to attract, and that's going to cause that alveolus to collapse. So to minimize that surface tension created by the water, our lungs secrete a substance called surfactant. Surfactant contains lipids that decrease that surface tension of water. And one situation where a lack of surfactant becomes a problem, and it can cause those alveoli to collapse, and it can prevent them from inflating, is in premature babies. And the reason it's a problem in premature babies is surfactant is not produced by the lungs in the developing fetus until right about the normal time of gestation, about just before 9 months. And so if a baby is born prematurely, it may be born before the lungs have had a chance to start producing surfactant. And if that happens, then their lungs will collapse, and that causes what's called infant respiratory distress syndrome. So if those alveoli collapse because there's not enough surfactant, then it's very difficult for those alveoli to become inflated again. And the newborn infant might not be able to get enough oxygen. And so, one thing you could do potentially is you could put that premature baby on a ventilator and artificially, force air in the lungs to ventilate it. The problem with that is that the lungs of a premature infant are very, very delicate. And you've got all those pulmonary capillaries associated with the alveoli. If you force lung into the air of a premature infant, then some of those capillaries can start rupturing, and you can get hemorrhaging in the lungs, which can damage the lungs. So you want to try to avoid that if you can. So one way to prevent that happening, if a pregnant mother is thought to be at high risk of giving birth prematurely, there's a shot that they can give to the mother that will pass across the placenta into the fetus that will cause the lungs of the fetus to start producing surfactant earlier on. And so if the baby is born premature, then they won't have that problem. They won't have that infant respiratory distress syndrome, which is also known as hyaline membrane disease, which refers to the appearance of the lungs when they collapse. Normally though, in adults, our lungs continually produce that surfactant, and so that decreases that surface tension, so that doesn't occur. So, normally, only the air that enters the alveoli is available for gas exchange, but not all the air that we take in gets there. There's about 150 milliliters of air that fills the conducting division of the respiratory system. Since there are no alveoli in the conducting division, that air is not available for gas exchange. And so that area that is filled with air, where gas exchange can occur, is called the anatomical dead air space. And in some pulmonary diseases, some of those alveoli may be unable to exchange gas because they either lack blood flow or the respiratory membrane has been thickened by either edema, which is fluid buildup in the alveoli, or fibrosis. Fibrosis is when those alveoli get damaged and scar tissue forms. The scar tissue is too thick for gas exchange to occur. So when that happens, that essentially increases the anatomical dead air space, which decreases the surface area available for gas exchange. So in summary, this section on ventilation, air enters and leaves the lungs as a result of pressure changes caused by changes in volume due to contraction of respiratory muscles. Quiet inspiration is due to contraction of the diaphragm and external intercostals. Quiet expiration is a passive process that just occurs when those inspiratory muscles relax and the chest wall recoils. We saw last week that the basic rhythm of breathing is produced by the ventral respiratory group. In what part of the brain is that in? What part of the brain is the respiratory centers?
The pons.
What was that?
The pons.
Thalamus? No.
The pons. The pons.
Well, there's one located in the pons, but where's the ventral and dorsal respiratory group located? Further down. It's the lowest part of the brain. What's the name for that? Medulla oblongata. Right. Medulla oblongata. That's where the ventral respiratory group is. Dorsal respiratory group is mostly just a relay center, and it receives signals from the pontine respiratory group, which can either increase ventilation or decrease ventilation. The dorsal respiratory group also receives input from the chemoreceptors, as well as the limbic system, which is the part of the cerebrum that controls emotions. Also, resistance decreases airflow, and it's determined by airway diameter, pulmonary compliance, and surface tension on the inside of the alveoli. That surface tension is normally reduced by surfactant. Not all air enters the alveoli. Some air remains in the anatomical dead air space, and it's unavailable for gas exchange. Now, we're going to do a lab this week that involves measurement of lung volumes. And these lung volumes are all part of that respiratory division of the lungs. And one way you can actually increase the anatomical dead air space of the respiratory system is by blowing through a tube, like breathing through a tube, like a snorkel. You know, snorkel you use when you're out swimming, and it's a tube that sticks up above the surface and you can breathe through it. Well, when you're breathing through a snorkel, you have to push that air in and out of that tube, and that essentially increases your anatomical dead air space, which means that when you're snorkeling and you're breathing through a snorkel tube, you actually have to work a lot harder to get enough air in your lungs to meet your body's demands. So you have to You have to use some of what's called your inspiratory and expiratory reserve volume of your lungs. And I think that would be a neat thing to do in lab. In fact, we could do it this week. It's not part of the lab exercise that's written up that we're going to do, but we could just take a piece of tubing and breathe through it and see what the effect would have on our respiratory volumes. It should actually decrease some of the lung volumes. Okay, let's do a couple of review questions here. Come up. Okay, so first one is, what's the very first part of the respiratory division? As air is going in, what's the first part of the respiratory division that air would meet? That code, by the way, is lung 1. That's a number 1. It's not an I. You probably see that, though. Count 35 people, so I need one more person to answer. There we go. Okay, let's look at everybody's response. Okay, nasal cavity has a little more than half. Respiratory bronchial has 35%. The correct answer is the first part of the respiratory division would be the respiratory bronchial. Nasal cavity would be the first part of the conducting division. That's part of the conducting, because there's no alveoli there. All right. Next question. Which phase of the respiratory cycle requires the expenditure of more energy? The inspiratory phase or the expiratory phase? You said inspiration, and that's correct. Okay. So why does the inspiratory phase require more energy? Why is it harder to take air in?
Muscles.
So you have to contract your inspiratory muscles. Expiration takes less energy because that occurs during quiet expiration anyway. That just occurs when the muscles relax. It doesn't take as much energy for muscles to relax as it does for them to contract. Okay. All right. So let's move on to the next section, and we won't be able to get through all of the next section, but we should be able to get through at least an introduction to it. Okay, so this next part of chapter 22 is concerned with gas exchange. And gas exchange refers to the diffusion of oxygen and carbon dioxide between the alveoli that contains air that came in from the atmosphere and the pulmonary capillaries in the lungs, and also between the systemic capillaries in the tissues of our body and the cells of our body. And the diffusion of oxygen and CO2, though, are in opposite directions. Since oxygen is something that our body needs, CO2 is basically a waste product that we need to get rid of. Okay? So oxygen and CO2 are always going in opposite directions. Now, there's another gas law that it's important to know to understand the factors that affect gas exchange, and this is Dalton's law. Dalton's law states that the total pressure of a mixture of gases is equal to the sum of the partial pressures of each individual gas that's in a mixture of gases. So as it turns out, air is not just made up of oxygen. Air is made up of a mixture of several different kinds of gases. It's made up of oxygen. Oxygen makes up approximately 23% of atmospheric air. Carbon dioxide. Carbon dioxide only makes up about 0.04% of atmospheric air. So CO2 is very low in the atmosphere. Nitrogen gas is another common gas in air. Nitrogen gas actually makes up the largest part of atmospheric air. Nitrogen gas makes up almost 78% of air. And finally, there's also water vapor, along with other gases, but these are the most common ones. Amount of water vapor in air, though, varies a lot depending on the humidity of the air. And so, to calculate the partial pressure of gas, of each gas, and you need to know that in order to predict gas exchange, you have to multiply the percentage of the gas by the total air pressure. And at sea level, the total air pressure is equal to 760 millimeters of mercury. Okay? So, oxygen makes up, I think I said 23%, I was off by a little bit. It actually makes up about 21%, or 20.9% of air. And so to calculate the partial pressure of oxygen, you have to multiply, you have to convert that percentage to decimal form. So you move the decimal point 2 places to the left, which is the same as dividing by 100. So you get 0.209, you multiply that by 760 millimeters mercury. And so the partial pressure of oxygen is 159 millimeters mercury. Okay? So it's a lot less than total air pressure because oxygen only makes up about 1/5 of air. All right? And you need to know that to be able to predict whether oxygen is going to move into our body or not. And you also need to know the partial pressure of oxygen in the blood, because gas exchange occurs by simple diffusion, and simple diffusion is determined by the difference in the partial pressure of gases in 2 different places. So, given that the atmospheric pressure is 760 millimeters mercury, and the partial pressure of CO2 is only 0.04%, what would be the partial pressure of CO2 in the atmosphere? Okay, I want you to try to calculate that. And I'll help you out. So to convert 0.04% to a decimal form, you have to move the decimal point 2 more places to the left. So that would be 0.0004. And then you have to multiply that by the total air pressure. And that will give you the partial pressure of CO2 in the atmosphere. Or another way you could do it, it'd give you the same answer. Multiply 760 times 0.04 and then divide your answer by 100. That should give you the same answer, right?
And the answer is 0. Because I just did the math.
So you have to multiply 0.0004 times 760. So what do you get?
3.04.
3.04?
3.0.
Yeah.
0.304. Okay, so that would be, so we could round that off to 0.3. So that would be the partial pressure of CO2 in the air. That's very low. So as long as the partial pressure of CO2 in the atmosphere is lower than the partial pressure of the CO2 in our blood, and the CO2 and partial pressure in our blood should be higher since our body is always producing it, then CO2 is going to diffuse out of our lungs and back out into the atmosphere. So, answer should have been 0.3. It looks like that's what most of you got, so good. That's the correct answer. Okay, so this just shows you how you do the calculations. Convert 0.04% to a decimal form, that's 0.0004. Times 760, you get 0.3 millimeters. So as I said, like any molecule of gas, a gas will diffuse from the area of high concentration to low concentration. So as long as the partial pressure in our blood is higher than the partial pressure of CO2 in the air, then CO2 will diffuse out of our blood and into the air in the alveoli. And then when we exhale, we blow that CO2 out. And that's how we keep the concentration of CO2 in our blood to a low enough level that we don't get acidosis. If you CO2 will dissolve in blood to form carbonic acid, which disassociates into hydrogen ions and bicarbonate. Those hydrogen ions then lower the pH of our blood. If our pH of our blood gets too low, then that disrupts enzymes in our body. Now, the air in our alveoli, as it turns out, actually has a lower concentration of oxygen than the atmosphere for a couple of reasons. It also has a higher concentration of CO2 than the atmosphere. So one of the reasons that the air in the alveoli has a lower partial pressure of oxygen than the atmosphere is that as we take in air through our respiratory tract, that air gets humidified by the mucous membranes in our nasal cavity and our airways. And when you add water to that air, that lowers the proportion of oxygen in the air in our lungs. Because you're essentially diluting that oxygen by adding more water vapor. Freshly inspired air is also a mixes with residual air left in our anatomical dead air space. And so that also dilutes the oxygen even further. And it's enriched by carbon dioxide from the residual air. And alveolar air continually exchanges oxygen and CO2 with the blood, and so that lowers the concentration of oxygen in the alveoli. So the partial pressure of oxygen, the partial pressure of CO2 in the alveoli, partial pressure of oxygen is only 104, and it's 40 millimeters mercury for CO2, rather than 159 millimeters mercury for oxygen in the atmosphere, and only 0.3 for CO2 in the air. So the air inside our alveoli has a lower concentration of oxygen because that oxygen gets diluted by water vapor when we breathe in, plus it gets diluted by the CO2 that's in that remains in the airways of our lungs. And the concentration of CO2 is actually much higher because CO2 is constantly diffusing out of our blood and into the alveoli. So the reason I mention this is because those changes in the partial pressure of those gases affect gas exchange, because the gas exchange depends upon the concentration gradient across the respiratory surfaces. So the partial pressure of oxygen in the alveoli is, instead of being 159 millimeters mercury, it's only 104, because it gets diluted by water vapor and CO2. The partial pressure of oxygen in pulmonary blood is only 40, because most of that oxygen that was in the blood gets used up by the cells of our body. Because that blood that's flowing to the lungs is venous blood that's oxygen poor. So, since the partial pressure of oxygen in the alveoli is higher than it is in the pulmonary blood, then that means oxygen is going to diffuse from the alveoli into the pulmonary blood. And it will increase the partial pressure of oxygen in the pulmonary blood. Now, the partial blood pressure of CO2 in the pulmonary blood is 46 millimeters, because the blood has picked up CO2 from the cells of our body. That's a waste product produced by our cells. Partial pressure of CO2 in the alveoli is 40, because partial pressure of the air that was taken in is fairly low. But since the CO2 is higher in the pulmonary blood than in the alveoli, that means that the CO2 is going to diffuse from the pulmonary blood into the alveoli, where it can be exhaled. Now, because the gradient for oxygen is much greater than the gradient of CO2, why isn't oxygen transported at a much greater rate than CO2 transport? We actually produce about as much CO2 as we do use up oxygen. Concentration gradient for oxygen is a lot higher than the concentration gradient for CO2. So why are the two transported about the same rate? Anybody know? There's a reason. And that's because the concentration gradient is not the only factor that affects the rate of diffusion. There are other factors. And the other factor that affects the rate of diffusion of those two respiratory gases is the solubility of those gases in water. Because all the respiratory surfaces are lined by a thin layer of water, including the inside of the alveoli. And so the reason that CO2 is transported at about the same rate as oxygen, even though the concentration gradient is much less, is because CO2 is much more soluble in water. So it dissolves into the thin layer of water lining the respiratory tracts a lot faster than oxygen does. And so it ends up being transported about the same rate as is oxygen, only in the opposite directions. And so the technical explanation for this has to do with another gas law, which you may or may not have talked about in chemistry. I'm not sure if you've covered all these or not, but there's another one explained by Henry's law that states that the amount of gas that dissolves in a liquid is proportional to the partial pressure gradient and the solubility of the gas in liquids. So in general, oxygen is not very soluble in water, but CO2 is much more soluble. And so that's why CO2 and oxygen are exchanged at about the same rate, just in opposite directions. So the partial pressure of oxygen in systemic capillaries is about 95 millimeters mercury. Partial pressure of oxygen in the tissues is only 40 because the cells of the tissues have used up a lot of the oxygen. But because there's a higher concentration of oxygen in the systemic capillaries than there is in the tissues, cells and tissues of the body, oxygen diffuses out of the blood and into the tissues. Likewise, CO2 levels in the tissues are higher than they are in the blood because the tissues are always producing CO2. And so CO2 is going to diffuse in the opposite direction, down its concentration. So the basic mechanism of gas exchange is very, very simple. It's just transported by simple diffusion, which just uses the random movement of gas molecules. So there's no carrier proteins or no active transport at all that's involved. It's just simple diffusion. Okay, we're out of time, so we'll stop here. We're going to be starting to talk about transport of gases in blood very, very soon.